Covalent bond. A covalent bond, also called a molecular bond, is a chemical bond that involves the sharing of electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs, and the stable balance of attractive and repulsive forces between atoms, when they share electrons, is known as covalent bonding. For many molecules, the sharing of electrons allows each atom to attain the equivalent of a full outer shell, corresponding to a stable electronic configuration. Covalent bonding includes many kinds of interactions, including sigma bonding, pi bonding, metal-to-metal bonding, agostic interactions, bent bonds, and 3-center two-electron bonds. The term covalent bond dates from 1939. The prefix CO means jointly, associated in action, partnered to a lesser degree, etc. Thus a covalent bond, in essence, means that the atoms share valence, such as is discussed in valence bond theory. In the molecule H2, the hydrogen atoms share the 2 electrons via covalent bonding. Covalency is greatest between atoms of similar electronegativities. Thus, covalent bonding does not necessarily require that the 2 atoms be of the same elements, only that they be of comparable electronegativity. Covalent bonding that entails sharing of electrons over more than 2 atoms is said to be delocalized. The term covalence in regard to bonding was first used in 1919 by Irving Langmuir in a Journal of the American Chemical Society article entitled The Arrangement of Electrons in Atoms and Molecules. Langmuir wrote that we shall denote by the term covalence the number of pairs of electrons that a given atom shares with its neighbors. The idea of covalent bonding can be traced several years before 1919 to Gilbert N. Lewis, who in 1916 described the sharing of electron pairs between atoms. He introduced the Lewis notation or electron dot notation or Lewis dot structure, in which valence electrons are represented as dots around the atomic symbols. Pairs of electrons located between atoms represent covalent bonds. Multiple pairs represent multiple bonds, such as double bonds and triple bonds. An alternative form of representation, not shown here, has bond-forming electron pairs represented as solid lines. Lewis proposed that an atom forms enough covalent bonds to form a full outer electron shell. In the diagram of methane shown here, the carbon atom has a valence of 4 and is, therefore, surrounded by 8 electrons, 4 from the carbon itself and 4 from the hydrogens bonded to it. Each hydrogen has a valence of 1 and is surrounded by 2 electrons, its own 1 electron plus 1 from the carbon. The numbers of electrons correspond to full shells in the quantum theory of the atom. The outer shell of a carbon atom is the n equals 2 shell, which can hold 8 electrons, whereas the outer shell of a hydrogen atom is the n equals 1 shell, which can hold only 2. While the idea of shared electron pairs provides an effective qualitative picture of covalent bonding, quantum mechanics is needed to understand the nature of these bonds and predict the structures and properties of simple molecules. Walter Heitler and Fritz London are credited with the first successful quantum mechanical explanation of a chemical bond in 1927. Their work was based on the valence bond model, which assumes that a chemical bond is formed when there is good overlap between the atomic orbitals of participating atoms. Atomic orbitals have specific directional properties leading to different types of covalent bonds. Sigma bonds are the strongest covalent bonds and are due to head-on overlapping of orbitals on 2 different atoms. A single bond is usually a sigma bond. Pi bonds are weaker and are due to lateral overlap between p orbitals. A double bond between 2 given atoms consists of 1 sigma and 1 pi bond, and a triple bond is 1 sigma and 2 pi bonds. Covalent bonds are also affected by the electronegativity of the connected atoms, which determines the chemical polarity of the bond. 2 atoms with equal electronegativity will make nonpolar covalent bonds such as HH. An unequal relationship creates a polar covalent bond such as with HCl. However, polarity also requires geometric asymmetry, or else dipoles may cancel out, resulting in a nonpolar molecule. There are several types of structures for covalent substances, including individual molecules, molecular structures, macromolecular structures, and giant covalent structures. Individual molecules have strong bonds that hold the atoms together, but there are negligible forces of attraction between molecules. Such covalent substances are usually gases, for example, HCl, SO2, CO2, and CH4. In molecular structures, there are weak forces of attraction. Such covalent substances are low boiling temperature liquids, and low melting temperature solids. Macromolecular structures have large numbers of atoms linked by covalent bonds in chains, including synthetic polymers such as polyethylene and nylon, and biopolymers such as proteins and starch. Network covalent structures contain large numbers of atoms linked in sheets, or three-dimensional structures. These substances have high melting and boiling points, are frequently brittle, and tend to have high electrical resistivity. Elements that have high electronegativity, and the ability to form 3 or 4 electron pair bonds, often form such large macromolecular structures. Bonds with 1 or 3 electrons can be found in radical species, which have an odd number of electrons. The simplest example of a 1-electron bond is found in the dihydrogen cation, H+2. 1-electron bonds often have about half the bond energy of a 2-electron bond, and are therefore called half bonds. However, there are exceptions. In the case of dilithium, the bond is actually stronger for the 1-electron Li+2 than for the 2-electron Li2. This exception can be explained in terms of hybridization and inner shell effects. The simplest example of 3-electron bonding can be found in the helium dimer cation, He+2. It is considered a half bond because it consists of only one shared electron. In molecular orbital terms, the third electron is in an anti-bonding orbital which cancels out half of the bond formed by the other 2 electrons. Another example of a molecule containing a 3-electron bond, in addition to 2 2-electron bonds, is nitric oxide, NO. The oxygen molecule, O2, can also be regarded as having 2 3-electron bonds and 1 2-electron bond, which accounts for its paramagnetism and its formal bond order of 2. Chlorine dioxide and its heavier analogues bromine dioxide and iodine dioxide also contain 3-electron bonds. Molecules with odd electron bonds are usually highly reactive. These types of bond are only stable between atoms with similar electronegativities. There are situations whereby a single Lewis structure is insufficient to explain the electron configuration in a molecule, hence a superposition of structures are needed. The same 2 atoms in such molecules can be bonded differently in different structures, resulting in a non-integer bond order. The nitrate ion is one such example with 3 equivalent structures. The bond between the nitrogen and each oxygen is a double bond in one structure and a single bond in the other 2, so that the average bond order for each NO interaction is 2 + 1 + 1/3 = 4/3. In organic chemistry, when a molecule with a planar ring obeys Huckel's rule, where the number of pi electrons fit the formula 4n+2, it attains extra stability and symmetry. In benzene, the prototypical aromatic compound, there are 6 pi bonding electrons. These occupy 3 delocalized pi molecular orbitals or form conjugate pi bonds in 2 resonance structures that linearly combine, creating a regular hexagon exhibiting a greater stabilization than the hypothetical 1,3,5 cyclohexatriene. In the case of heterocyclic aromatics and substituted benzenes, the electronegativity differences between different parts of the ring may dominate the chemical behavior of aromatic ring bonds, which otherwise are equivalent. Certain molecules such as xenon difluoride and sulfur hexafluoride have higher CO ordination numbers than would be possible due to strictly covalent bonding according to the octet rule. This is explained by the 3-center 4-electron bond model, which interprets the molecular wave function in terms of non-bonding highest occupied molecular orbitals in molecular orbital theory and resonance of sigma bonds in valence bond theory. In 3-center 2-electron bonds, 3 atoms share 2 electrons in bonding. This type of bonding occurs in electron-deficient compounds like diborane. Each such bond contains a pair of electrons which connect the boron atoms to each other in a banana shape, with a proton in the middle of the bond, sharing electrons with both boron atoms. In certain cluster compounds, so-called 4-center 2-electron bonds also have been postulated. After the development of quantum mechanics, 2 basic theories were proposed to provide a quantum description of chemical bonding: valence bond theory and molecular orbital theory. A more recent quantum description is given in terms of atomic contributions to the electronic density of states. The two theories represent two ways to build up the electron configuration of the molecule. For valence bond theory, the atomic hybrid orbitals are filled first to produce a full valence configuration of bonding pairs and lone pairs, followed by a linear combination of contributing structures if there are several of them. In contrast, for molecular orbital theory, a linear combination of atomic orbitals is performed first, followed by the filling of the resulting molecular orbitals by the Aufbau principle. The two approaches are regarded as complementary, and each provides its own insights into the problem of chemical bonding. As valence bond theory builds the molecular wave function out of localized bonds, it is more suited for the calculation of bond energies and the understanding of reaction mechanisms. As molecular orbital theory builds the molecular wave function out of delocalized orbitals, it is more suited for the calculation of ionization energies and the understanding of spectral absorption bands. At the qualitative level, both theories contain incorrect predictions. Simple valence bond theory correctly predicts the dissociation of homonuclear diatomic molecules into separate atoms, while simple molecular orbital theory incorrectly predicts dissociation into a mixture of atoms and ions. On the other hand, simple molecular orbital theory correctly predicts Huckel's rule of aromaticity, while simple valence bond theory incorrectly predicts that cyclobutadiene has a larger resonance energy than benzene. Although the wave functions generated by both theories at the qualitative level do not agree and do not match the stabilization energy by experiment, they can be corrected by configuration interaction. This is done by combining the valence bond covalent function with the functions describing all possible ionic configurations, or by combining the molecular orbital ground state function with the functions describing all possible excited states using unoccupied orbitals. It can then be seen that the simple molecular orbital approach gives too much weight to the ionic structures while the simple valence bond approach gives too little. This can also be described as saying that the molecular orbital approach neglects electron correlation while the valence bond approach overestimates it. Modern calculations in quantum chemistry usually start from a molecular orbital rather than a valence bond approach, not because of any intrinsic superiority in the former but rather because the MO approach is more readily adapted to numerical computations. Molecular orbitals are orthogonal, which significantly increases feasibility and speed of computer calculations compared to non-orthogonal valence bond orbitals. However, better valence bond programs are now available. In COOP, COHP, and BCOOP, evaluation of bond covalency is dependent on the basis set. To overcome this issue, an alternative formulation of the bond covalency can be provided in this way. The center mass cm of an atomic orbital nlmlms, with quantum numbers n, l, ml, ms, for atom A is defined as, where GaNLMLms is the contribution of the atomic orbital NLMLms of the atom A to the total electronic density of states G of the solid, where the outer sum runs over all atoms A of the unit cell. The energy window is chosen in such a way that it encompasses all relevant bands participating in the bond. If the range to select is unclear, it can be identified in practice by examining the molecular orbitals that describe the electron density along the considered bond. The relative position nala NBLB of the center mass of NALA levels of atom A with respect to the center mass of NBLB levels of atom B is given as, where the contributions of the magnetic and spin quantum numbers are summed. According to this definition, the relative position of the A levels with respect to the B levels is, where, for simplicity, we may omit the dependence from the principal quantum number n in the notation referring to nala NBLB. In this formalism, the greater the value of CAB, the higher the overlap of the selected atomic bands, and thus the electron density described by those orbitals gives a more covalent AB bond. The quantity CAB is denoted as the covalency of the AB bond, which is specified in the same units of the energy E.